We've now reached the third part of the book, and we start with Chapter 7 in our tour of applications of nanoscience, electrons in nanostructures. We're going to begin with background and talk about how the free electron model explains many of the properties of materials. We'll then talk about what happens when these free electrons are put into materials with a periodic potential, i.e. crystals, and we'll develop band structure. We'll talk about the complications of band structure in 3 dimensions. And then we turn to some genuine nanoscience. What happens when electrons pass through very tiny constrictions and introduce the very useful idea of the Landau resistance? What happens when electrons localize on a nanostructure? This is the Coulomb blockade. And then the other extreme, when electrons pass through a nanostructure without localizing on it, resonant tunneling. And finally, we'll say a little bit about electron localization and system size. Materials have an unbelievably large range of electronic properties. The appropriate parameter to discuss these in terms of is the resistivity of a material. So if we take a rod of material and consider that it has a length L and some cross-sectional area A, then we know that the resistance goes up with L and down with A. The constant of proportionality is the resistivity. So this has units of meters to the -1. The units of rho are therefore ohm meters. Ohm centimeters are often used in the semiconductor industry. Look at the incredible range on this table. All the way from 10 to the -8 ohm meters for some conductors up here, to 10 to the +15 or 16 ohm meters for insulators down here on the table. This is an incredible range. In fact, we'll see this range is controlled by the number of electrons available to transport electricity. It doesn't take many electrons in a solid to carry current. So if you imagine that this is the wire from your outlet on the wall to your electric kettle, and it's carrying a current of, let's say, 1 amp, this is equal to about 10 to the 18, somewhat more than 10 to the 18 electrons per second. There's probably a gram of copper in this wire, and so the amount of copper electrons is going to be roughly the atomic weight of copper, which is approximately 60, 1/60th of that in 1 gram, times Avogadro's number. If each copper atom gives 1 electron, it actually gives 2. That's 6 times 10 to the 23. And so you can see that something like 10 to the 22 electrons are available in this wire, and only 1 in 10 to the 4th passes through the wire in heating your electric kettle. So let's try and understand things a little better with a model of this resistivity. Before we do that, though, let's turn to the idea of free electrons in a solid. It's almost an absurd idea. We know, 1, that electrons are fermions, and 2, that electrons have a charge of -e on them, and therefore a very strong Coulomb repulsion when they come close. How on earth can electrons be considered to be free in condensed matter containing Avogadro's number of electrons in a liter? The theory for this is due to Landau, and it's called Fermi Liquid theory. So I'm going to just outline some of the ideas here. The electrons are distributed in energy according to the Fermi distribution, which we talked about in Chapter 3. So here is the average thermal occupation, and here is energy. This is unity up to the Fermi energy, and then drops to 0 at T equal to 0. At a finite temperature, this distribution is smeared out like this, where this width here is on the order of kT, which at 300 degrees we know is about a 40th of an electron volt, whereas EF for a typical metal is on the order of 5 electron volts. Now, let's think about what happens to an electron that has been excited from below the Fermi energy to above it, so it leaves a hole behind, and here is an electron that's been excited from below the Fermi energy. This electron excited from below the Fermi energy will see around it mainly electrons that are still below the Fermi energy, because it's one of the few that are above it. So most of the electrons it can interact with are below the Fermi energy. Now, in order to interact with that electron and change its momentum and direction, so I'm now going to make this diagram one of momentum. So instead of Fermi energy, I'm going to put down Fermi wave vector, which we'll define a little later. It's simply the wave vector that corresponds to the Fermi energy. In order to conserve energy and momentum, when this electron interacts with this one, let's say this one is excited, the only place it's got to go is outside the Fermi sphere, because the Pauli exclusion principle says it can't be scattered to any states inside the sphere. This electron then will also in general go outside the Fermi sphere. But the number of combinations that can satisfy energy and momentum while remaining in a small area like this, 0.25 eV compared with 5 eV close to the Fermi energy, is essentially zero. So these particles, these excitations now, called quasi-particles, behave as though they are free simply because scattering is very difficult near the Fermi energy. When you work out the math, it turns out that they have an energy which is related to the absolute energy minus the Fermi energy, and this energy turns out to be derived from h bar squared times their momentum squared all over 2m star, where m star is not equal to the free electron mass, it's an effective electron mass. They have the same charge and the same spin as electrons, and therefore these quasi-particles, electrons or holes, really do behave as though they were free particles, providing they're close to the Fermi energy. So, before Landauer, Drude just said, well, let there be free electrons on a solid without thinking too hard about it, and he reasoned that these electrons would have some average thermal velocity v, and they would travel for some time, tau, before being scattered, and then they do the same again and get scattered, and so that the average acceleration would be v over tau. Mass times acceleration, according to Newton's second law, is force, which is the electronic charge times E. I've got a minus sign on this slide because I'm using absolute value of E on the slide. So here is Newton's second law. The Ohm's law is defined by the current density, so this is current over area, is equal to the conductivity, this is just 1 over the resistivity, times the electric field, that's just the applied volts per meter. So this is V equals IR, but just expressed a little differently. Given that the current density is defined to be the number of carriers times their charge times the average velocity, one can show very quickly that the conductivity, which is 1 over the resistivity, is given by n e squared tau over m. This is the Drude result. If one takes the known resistivity for copper, one predicts that tau is around about 3 times 10 to the minus 14 seconds, and this agrees with experiments, so hooray for Drude. However, if you use the equipartition theorem, of course this could be x, y, or z, and calculate the distance that this time corresponds to using this thermal velocity, sorry, I should have made that a velocity, you discover that the mean free path, the distance between scattering events, is calculated to be about a nanometer, and yet it's measured to be tens to hundreds of nanometers. So Drude theory needs improvement.